Good morning, welcome to lecture 9. This is our first of 4 lectures about calculus. This week we're going to be talking about limits, continuity and differentiation. First, consider the function x squared minus 1 over x minus 1. The domain of this function is the open interval between minus infinity and 1, union the open interval from 1 to infinity. So in other words, the domain is the whole real line except x equal to 1. And the graph of the function looks like this. We have a hole when x is equal to 1 because the function is not defined when x is equal to 1. But I want to ask the question, how does f behave when x is close to 1? Well, which numbers are close to 1? 0.9 and 1.1 are close to 1. We can calculate f at 0.9, put 0.9 into our formula. 0.9 squared minus 1 divided by 0.9 minus 1, and we obtain 1.9. Or if we put 1.1 into the formula, then we get f of 1.1 is 2.1. Okay, what about if we look even closer to 1? 0.99 and 1.01 are even closer to 1. Put these numbers into the function and we calculate 1.99 and 2.01. So how does f behave when x is close to 1? It looks like if x is close to 1, then f of x is going to be close to 2. Let's look even closer. How about 0.999 and 1.201? Again, looks like we're getting closer and closer to 2. It looks like if x is close to 1, then f of x is close to 2. We have a way of writing this in mathematics. In mathematics, we write this as the limit as x tends to 1 of f of x is equal to 2. That means as x gets closer and closer to 1, but actually never gets to 1, then f of x gets closer to 2. Go back to the graph of the function. We are saying that the limit as x tends to 1 of f of x is equal to 2. But for this function, f is not defined at x equal to 1. Let's look at a different function. The function g, I'm going to be defined to be the same as f if x is not equal to 1, and I'm going to define g of x is equal to 1 if x is equal to 1. So again, we have a hole up here, and we have a spot or a dot at 1, 1. Again, we're going to say the limit as x tends to 1 of g of x is equal to 2. Why? Because if x is close to 1 but actually not equal to 1, then g of x is close to 2. If x is close to 1 but not equal to 1, then we're up here close to the hole, so g of x is close to 2. This is an example where the value of g of 1, is not equal to the limit as x tends to 1 of g of x. And one more function, the function h of x equal to x plus 1. This function doesn't have any holes in. How does h behave if x is close to 1 but not equal to 1? H is close to 2, so we write that the limit as x tends to 1 of h of x is equal to 2. And for this function, the limit is the same as the value of the function at 1. That was 3 different functions which had the same limit but with different behaviors of the value of the function at 1. For my next example, think about the identity function, in other words, the function f of x is equal to x. Choose some number x0, any number x0, and then I want to ask the question, how does the function behave if x is close to x0? Well, if x is close to x0, then f of x, which is equal to x, is also close to x0. So we can say that the limit as x tends to x0 of x is equal to x0. A constant function. Here's a function which is always equal to 13. Choose any x0, and then I want to ask the question, how does the function behave if x is close to x0? Well, the function is always equal to 13. Doesn't matter if x is close to x0 or not close to x0, 13 is always 13. The limit as x tends to x0 of 13 is equal to 13. Now, sometimes limits do not exist. I'm going to show you two functions which do not have a limit at 0. First function u is equal to 0 if x is strictly less than 0 and equal to 1 if x is greater than or equal to 0. My second function v of x is equal to 0 if x is less than or equal to 0 and equal to sine 1 over x if x is greater than 0. First, let's look at the function u. This graph looks like this. And I'm stating that the limit as x tends to 0 of u of x does not exist. Why? Well, what happens to the function if x is close to 0 but not equal to 0? First of all, if x is close to 0 but less than 0, so in other words, if we're on the left, how does the function behave? The function is always equal to 0. And if x is close to 0 but bigger than 0, so looking at this part now, how does the function behave? The function is always equal to 1. But 0 is not close to 1. That means there doesn't exist one number that the function is always close to if x is close to 0. So the limit as x tends to 0 cannot exist. And for the second function, the limit as x tends to 0 of v of x does not exist. Why? Because this function oscillates up and down, up and down, up and down too quickly if x is positive and x tends to 0. There does not exist one number that the function is always close to. Now, for the first theorem of today, I want to give the limit laws. In this theorem, L, M, C, and K are going to be numbers. F and G are going to be functions. And we're going to assume that the limit as x tends to c of f of x is L, and the limit as x tends to c of g of x is equal to M. Then rule number one is called the sum rule. This says the limit of f plus g is equal to the limit of f plus the limit of g. So in other words, if we see a plus inside a limit, we can cut it just here into two smaller limits. Rule number 2 is called the difference rule. Same idea, but instead of a plus, we have a minus sign. The limit of f plus g, so the limit is f minus g, is equal to the limit of f minus the limit of g. So again, if we have a minus sign inside a limit, we can cut it here into two smaller limits. Rule number 3 is called the constant multiple rule. Anytime we have a number k inside a limit, we can take the number outside. The limit of kf is equal to k multiplied by the limit of f. And if we have two functions multiplied together, we have the product rule. the limit of f multiplied by g is equal to the limit of f multiplied by the limit of g. So again, if we have two functions multiplied together, we can cut it here and have limit multiplied by limit. For the quotient rule, we need to be a little bit careful. We need to make sure we're not dividing by 0. Then the quotient rule says the limit of f divided by g is equal to the limit of f divided by the limit of g. Rule number 6 is called the power rule. If n is a natural number, then the limit of f to the power n is equal to the limit of f all to the power n. So in other words, it doesn't matter if we put brackets here. First calculate, sorry, let me redo that. It doesn't matter if we put brackets here. First calculate f to the power n, then take the limit. That's exactly the same as putting brackets just here. First calculate the limit of f and then do it all to the power n. And then the final rule is called the root rule. And again, we need to start by being a little bit careful. We need the nth root of L to exist. But what do I mean by that? Well, we know the square root of -2 doesn't exist. So we need to just check that the nth root of L exists. Then the limit of the nth root of f is equal to the nth root of L, or the nth root of the limit of f. Okay, we have these 7 rules. How do we use them? We can use them to calculate limits like this. Find the limit as x tends to 2 of x cubed plus 4x squared minus 3. And the calculation goes like this. I have a function divided by a function, so first I want to use the quotient rule to write this as the limit of x to the power 4 plus x squared minus 1 divided by the limit of x squared plus 5. Then in both the top and the bottom I have pluses and minuses. I want to use the sum rule and the difference rule to break the limit into smaller limits at every plus and at every minus. So that's limit of x to the power 4 plus the limit of x squared minus the limit of 1 divided by limit of x squared plus limit of 5. By the power rule, the limit of x to the power 4, that's the same as limit of x all to the power 4. And limit of x, as x tends to 5, is just 5. So we get 5 to the power 4. Likewise, the limit as x tends to 5 of x squared is 5 squared. The limit as x tends to 5 of 1 is 1, and so on. We obtain the answer 649 divided by 30. But isn't there an easier way to do things like this? And the answer is yes. If we have a polynomial function, then the limit as x tends to c of p of x is always p of c. And if we have a rational function, so that's polynomial divided by polynomial, and as long as we're not dividing by 0, the limit of the rational function p of x divided by q of x is equal to p of c divided by q of c. So that makes things easier. If we're given a limit like this, we don't need to deal with the limit rules. We can just use the previous theorem. We have a polynomial divided by a polynomial, and because we're not dividing by 0, all we need to do is replace every x by -1, and then find that we get 0 divided by 6. But what do we do if we do have a 0 on the bottom? how do we calculate the limit as x tends to c of p of x divided by q of x if q of c is equal to 0? The answer is we cancel the zeros algebraically. For example, calculate the limit as x squared plus x minus 2 divided by x squared minus 2. If we just put x equal to 1 in here, then we're going to get 0 divided by 0. And that's not something we want. We never, never, never want to get 0 divided by 0, because 0 divided by 0 is not a number. So instead, what we want to do is we want to try to factor the polynomial on the top and the polynomial on the bottom. Remember, if we're doing limit as x tends to 1, then we're thinking that x is close to 1, but x is not equal to 1. So anytime we're doing a calculation like this, we can always assume that x is not equal to 1. And then we can factorize our rational function into x minus 1, x plus 2 divided by x, x minus 1. And the x minus 1's cancel, and we just get x plus 2 divided by x. So that means the limit that we want to calculate is the same as the limit as x tends to 1 of x plus 2 divided by x. And this time, we're not going to be getting divided by 0. If we replace every x by 1, then we do not get a 0 on the bottom, so we can just use the quotient rule to get 3 divided by 1. My next idea is called the sandwich theorem. Let's suppose we got 3 functions like this, where f is the smaller function, g is a middle function, and h is the bigger function. And we want f and h to have the same limit as x tends to c. Then the conclusion is the blue function, which is sandwiched or squashed between the other two, must also have the same limit. Now, we're only interested in what happens close to c. It doesn't matter what happens all of the way over on the left. So if I continue the graphs, it doesn't matter if f is bigger than h all the way over to the left. That doesn't matter. All we care about is what happens close to c. So the theorem says this. First of all, suppose f is less than or equal to g is less than or equal to h for all x close to c. We're doing limits, so we don't care what happens at c, we just want it to be true close to c. And suppose that f and h have the same limit as x tends to c. Then the sandwich theorem tells us that the function which is squashed or sandwiched in the middle also has the same limit. And we can use that to solve problems like this. The question tells us that this inequality is true for all x close to 0, but x not equal to 0. And then we're asked to calculate the limit as x tends to 0 of x sine x over 2 minus 2 cos x. So what we're going to do is we're going to calculate the limit of the function on the left, and we're going to calculate the limit of the function on the right, and then we're going to use the sandwich rule to say that the function in the middle must have the same limit. What is the limit of the function on the left? The limit of 1 minus x squared over 6. We can just replace x by 0 to get 1. And what is the limit of the function on the right? Limit of what? A number is just a number. So limit of 1 is 1. So we have limit 1 on the left, limit 1 on the right. The sandwich theorem says the function in the middle is squashed between a function of limit 1 and a function of limit 1. So the function in the middle must have the same limit. The function in the middle must have the limit 1. A similar theorem, if we have two functions, f and g, and if f is always less than or equal to g, close to c, again, we don't care what happens all the way on the left, we don't care what happens all the way on the right, we just care that close to c, f is less than or equal to g. Suppose that both the limit as x tends to c of f exists, the limit as x tends to c of g exists, then the limit of f must be less than or equal to the limit of g. I'll leave that for you to think about. Let's move on to thinking about continuity. Some functions, we can draw their graph without lifting our pen off the paper. If I wanted to draw this graph, I could put my pen down onto the paper, I can draw the graph all in one go without having to lift my pen up. But for other functions, if we want to draw the graph, we can draw part of the graph. I can start on the left, I can put my pen down and draw along. But when I get to C, I'm going to have to lift my pen up and then put it back down onto the paper and then carry on drawing. If we have to lift our pen off the paper when we draw a graph, then the function is not continuous. But this is mathematics. We need to be more precise than that. So we define a continuous function like this. A function f with domain D is continuous at the point C and D if these three rules are satisfied. Rule number one, we must have that f of c exists. Rule number two, we need to have the limit as x tends to c of f of x exists. And rule number three, these two numbers must be equal. If f is not continuous at c, then we say that f is discontinuous at c, or equivalently, we say that c is a point of discontinuity of f. So for example, have a look at this function. Consider the function f with domain closed interval from 0 to 4, which has the graph drawn above. Where is this function continuous and where is it discontinuous? Well, first of all, at 0. Is the function continuous at 0? The answer is yes. Why? Because f of 0 exists. The limit as x tends to 0 of f of x exists. And both of these numbers are equal to 1. Is the function continuous between 0 and 1? Yes. Why? Well, intuitively, because we could draw this part of the graph without lifting our pen up. All of the graph between x is 0 and x is equal to 1, I could draw this in one piece. Or in terms of mathematics, because f of c exists, the limit as x tends to c of f of x exists, and these two numbers are equal. Is the function continuous at c equal to 1? No. Why? Intuitively, because if we're drawing the graph, we have to lift our pen up and then put it back onto the paper at 1. In terms of mathematics, it's because the limit as x tends to 1 of f of x does not exist. Why? Because if we're on the left, if x is close to 1 and we're on the left, then we're going to be close to 0. But if we're on the right, if x is close to 1 but on the right, then we're close to 1, and 0 is not close to 1. So the limit as x tends to 1 of f of x does not exist. Next, between 1 and 2, is it continuous? Yes. Is it continuous at 2? No. Why? Well, the limit exists. The limit as x tends to 2 exists and is equal to 1. And the function is defined here. f of 2 is equal to 2. But these numbers are not the same, so the function is not continuous here. Is the function continuous between 2 and 4? Yes. Is it continuous at 4? No. Next example. The function f of x is equal to the square root of 4 minus x squared, which has domain closed interval from -2 to 2. This function is continuous at every c between -2 and 2. Intuitively, we can draw the graph in one go without having to lift our pen up. In terms of mathematics, choose any c between -2 and 2. The limit exists, f of c exists, and these two numbers are the same. The function g, which is defined to be equal to 0 if x is less than 0, or 1 if x is greater than or equal to 0. We can see that this function has a point of discontinuity at c equal to 0. We can see that g is continuous at every other point. A function h this function is continuous between -infinity and 1, between 1 and 2, and between 2 and infinity, but it has points of discontinuity at c equal to 1 and c equal to 2, as we can see from the graph. If a function is continuous everywhere, is continuous at every point in its domain, then we just say that the function is a continuous function. Time for another theorem. Let's suppose we have two functions f and g which are continuous at a point c. Then we could add them together and we still have a continuous function. We can take the difference, f minus g, continuous. Multiply it by a number, still continuous. F multiplied by g, continuous function, multiplied by continuous function, continuous. F divided by g is continuous, but just be careful. It's continuous as long as we're not dividing by 0. F to the power n, continuous. For the nth root, we need to be a little bit more careful. So this is just being careful. We need it to exist close to c and at c. Then, as long as we've done that check, the nth root of a continuous function is also continuous. So that means every polynomial is continuous. Every rational function is continuous as long as we're not dividing by 0. As long as q of c is not equal to 0, p of x divided by q of x is continuous at c. Sine and cos are continuous. Let's talk about composites. G composed with f of x means first we do f of x, and then after we've done that calculation, we do g of f of x. So we can think of that like this. We can think of we're starting at c, and then we do the function f to get to a point f of c, and then we do the second function g to get to g of f of c. We have a theorem which says if f is continuous at c, and if g is continuous at f of c, then g composed of f is continuous at c. So first do a continuous function to get a new number f of c, and then do another continuous function of that to get g of f of c. If we're doing continuous function of a continuous function, then we have a continuous function. So for example, show that the square root of x squared minus 2x minus 5 is continuous on its domain. Well, square root of t is continuous by a theorem we've had earlier. t is continuous. Take the square root of continuous, so we get continuous. Okay. X squared minus 2x minus 5 is continuous because all polynomials are continuous. So we're doing continuous function of a continuous function. That's a continuous function. Show that x to the power 2 over 3 divided by 1 plus x to the power 4 is continuous. Well, x to the power 2 over 3 is continuous by Theorem. 1 plus x to the power 4 is continuous. 1 plus x to the power 4 is not equal to 0, so we have continuous function divided by a continuous function which is not equal to 0. We have a continuous function. Theorem. If g is continuous at x equal to b, and if the limit as x tends to c of f of x is equal to b, then the limit as x tends to c of g of f of x is equal to g multiplied by, so g of the limit as x tends to c of f of x. So what this theorem says is, if we have continuous functions, then we're allowed to swap the positions of the function and the limit. And we can use that to calculate limits like this. I'm starting with the limit as x tends to pi over 2 of cos of something. But cos is a continuous function. Anytime we have a continuous function, we're allowed to swap the limit and the function. So instead of writing limit of cos, we could write cos of limit. So that gets us to here. Sum rule, limit of x squared plus the limit of sine of something. Sine is continuous. Anytime we have a continuous function, we're allowed to swap the positions of the limit and the function. So instead of writing limit of sine, we could write sine of limit. And then after we've done that, we can replace all of the x's by pi over 2 and get our answer. Our final topic for this week's lesson is the topic of differentiation. I imagine you've seen this road sign while you're driving around. What does this mean? This means that the road is sloping upwards. It means that if we travel forward by 100 meters, the road is going to go up 3 meters. In mathematics, we write the slope of this road or slope of this line as 3 divided by 100. More generally, the slope of this green line is b divided by a. The slope of this green line, we draw our triangle, the width of the triangle is 3 and the height of the triangle is 3, so the slope is 3 divided by 3 or 1. The slope of this line, the triangle has height 4 and width 2, so we do 4 divided by 2. The slope of this green line is equal to 2. Here's a green line which is sloping downwards. To show that it's sloping downwards, we say that our triangle has height minus 2. And then we can say that the slope of this line is minus 2 divided by 4, or minus a half. Okay, so that's slopes of lines. Anytime we have a line, draw the triangle, measure the height, measure the width, and then do the calculation to get the slope of the line. But what if we don't have a straight line? What if we have a curve? What is the slope of this curve when x is equal to x0? Well, what we can do is we can draw a green line which just touches the blue curve and which has the same slope at this point. This green line is called the tangent line at x equal to x0. And because it's a line, we can draw our triangle and then calculate the slope of the tangent line. We say that the slope of the blue curve at x equal to x0 is the same as the slope of the tangent line at x equal to x0. So for example, if we had the function y is equal to x squared, we might ask, what is the slope of y is equal to x squared when x is equal to 1? And so we draw our tangent line, we measure the slope of the tangent line, and we find 2. So the slope of the blue curve when x is equal to 1 is 2. When x is equal to 0, we can draw a tangent line, measure the slope of the tangent line, and we can see that the slope is 0. So the slope of the blue curve when x is equal to 0 is equal to 0. And one more. The slope of the blue curve when x is equal to 2 is the same as the slope of the red line, and that has slope equal to 4. So what we could do is we could draw the graph, we could carefully draw the tangent line, and then we can draw a triangle and measure its height and measure its width. But is there a better way to calculate the slope of the tangent line to a function? And the answer is yes. Let's just take some function y is equal to f of x and look at its tangent line. We want to calculate the slope of this tangent line, but actually there's an easier slope to calculate. Instead, we could calculate the slope of this orange line. The orange line has roughly the same slope as the tangent line. Calculating the slope of the orange line is going to be easy because we draw our triangle. We know our width of this triangle is h, and we know the height of this triangle, f of x0 plus h minus f of x0. So the slope of the orange line is going to be height of the triangle divided by width of the triangle. F of x0 plus h minus f of x0 divided by h. Okay, so for any function f, we could calculate the slope of the orange line. But look what happens as we make h smaller. As h gets smaller and smaller, the slope of the orange line is getting closer and closer to the slope of the green line. In fact, we can say if h is very, very small, then the slope of the green line is approximately equal to the slope of the orange line. And then we have a formula for that. If h is close to 0, then the slope of the tangent line, which is the one we want, is close to f of x0 plus h minus f of x0 divided by h. But we've been talking about close to already today. Anytime we start thinking about what happens if something is close to something, we want to be talking about limits. So that motivates this definition. The derivative of a function f at the point x0, that's another way of saying the slope of the graph of f, is the limit as h tends to 0 of the slope of the orange line, f of x0 plus h minus f of x0 divided by h, if this limit exists. And we call the derivative of a function f prime. For example, consider the function g of x is equal to 1 over x as long as x is not equal to 0. Calculate the derivative or the slope of this function at some point x0. Well, we're going to start with our formula. We want to calculate g prime, and g prime is equal to the limit as h tends to 0 of, and then we have the slope of the orange line, g of x0 plus h minus g of x0 divided by h. We need to take our formula 1 over h and put that in here, simplify it, and then take the limit. So first of all, g of x0 is 1 over x0. Replace every x by x0 to get 1 divided by x0. And g of x0 plus h, take 1 over x and replace the x by x0 plus h to get 1 over x0 plus h. We need to simplify this. And just as at school, when you were taught to calculate, say, a half minus a third, we have to write everything over the same denominator. We have to write this as 3 over 6 minus 2 over 6. So same idea here. I want to write everything over the same denominator. So everything over x0, x0 plus h. And then after I've done that, x0 minus x0 will cancel, and then h on the top will cancel with h on the bottom, and we end up with minus 1 over x0, x0 plus h. At this point, because we're not dividing by 0, we can replace h by 0 to get minus 1 over x0 multiplied by x0. And then we're finished. The derivative of 1 over x at x0 is minus 1 over x0 squared. And I can show you the graph of this function. For example, if x0 is equal to 2, put number 2 in here, the slope of the green line, and therefore the slope of the blue curve, when x is equal to 2, is minus 1 divided by 2 squared, so minus a quarter. Or if we put in x0 is equal to minus 1, we get minus 1 divided by minus 1 squared, which is minus 1. The slope of this red line, and therefore the slope of the blue curve, when x is equal to minus 1, is equal to minus 1. A definition. If f prime at x0 exists, then we say that f is differentiable at x0. If our function is differential at every point in its domain, then we just say that the function is differentiable. If a function is differentiable, then we have a new function called f prime. F prime is called the derivative of f. Let's do another example. Differentiate f of x is equal to x over x minus 1. In other words, we're asked to find the derivative of f. We're asked to find f prime. So we take our formula. The formula that we're going to be using is f prime of x is equal to, the limit as h tends to 0, of f of x plus h minus f of x divided by h. Just as before, we're going to put our formula for f in, we're going to simplify it, and then we're going to take the limit. So f of x, that's just x over x minus 1. For f of x plus h, we take our formula x divided by x minus 1, and we replace every x by x plus h. So x plus h on the top, and then x plus h on the bottom, minus 1. Like the previous example, we need to simplify this, and to simplify this, we need to put everything over the same denominator. Multiply out the top and cancel the terms, and we just end up with minus h on the top, but that h cancels with the h on the bottom. Minus 1 divided by x minus 1, x plus h minus 1. At this point, we can see that we're not dividing by 0 anymore, so we can replace the h by 0, and then we get our final answer, minus 1 over x minus 1 squared. Let's talk about notation. There's many ways to write the derivative of y is equal to f of x. These ones all mean the same. We could write f prime at x, or y prime, or dy dx, or df dx, or d dx of f of x, or y dot, or f dot of x. Why do we have so many notations? Well, because calculus was started by two men, Leibniz and Newton, and they both claimed that they were the one that invented calculus first. They argued about this and they grew to hate each other. So Isaac Newton used f dot and y dot notation. Gottfried Leibniz used the df dx and dy dx notation. Later on, Lagrange introduced the f prime and y prime notation. If we want to calculate, or if we want to write down the derivative of y is equal to f of x at a particular point, at the point x is equal to x0, we can write any of these. We could write f prime at x0, or dy dx at x equal to x0, or df dx at x equal to x0, or d dx of f of x at x equal to x0. So for example, if we have the function u of x is equal to 1 over x, and if we want to calculate this at 4, we could write u prime at 4. That's the same as the derivative of 1 over x at x equal to 4. We've done this already. We know that the derivative of 1 over x is minus 1 over x squared. So we have minus 1 over x squared at x equal to 4. That's minus 1 over 4 squared, or minus 1 over 16. Show that the absolute value function is differentiable on the open interval from minus infinity to 0, and differentiable on the open interval from 0 to infinity, but is not differentiable at x equal to 0. Well, we can do our calculation like this. If x is positive, then absolute value of x is just the same as x. So that's limit of x plus h minus x divided by h. The x's cancel, we get h over h. The h's cancel, and we just end up with 1. We're doing the limit as h tends to 0 of 1, which of course is equal to just 1. If x is less than 0, then the absolute value of x is equal to minus x. And I'll leave it for you to check that we then get minus 1. Because these limits exist, this proves that f is differentiable between minus infinity and 0, and between 0 and infinity. But what happens at 0? If we try to do the limit as h tends to 0 of the absolute value of 0 plus h minus the absolute value of 0 divided by h, we're doing the limit as h tends to 0 of absolute value of h divided by h. But absolute value of h divided by h is either plus 1 or minus 1, depending on if h is a positive number or a negative number. And that limit does not exist. That proves that our function is not differentiable at 0. Okay, so here's a function which does not have a derivative. When does a function not have a derivative at a point? Like the previous example, if we have a corner on our graph, then f prime at x0 does not exist. If we had a cusp, something like this picture, then again, f prime at x0 does not exist. If I had a vertical tangent, then the derivative does not exist at that point. If there's a discontinuity like this, then f prime at x0 does not exist. Or if there's a discontinuity like this, then f prime at x0 does not exist. So if there's a discontinuity, then the derivative does not exist. Using the ideas from part 1, when we talked about symbolic logic, f implies q is the same as not q implies not p. So if a discontinuity implies not differentiable, change that around. Logically, that is the same as saying if f has the derivative at x0, then f is continuous at x0. And then that is the end of this week's lesson. Next week, we're going to be talking more about differentiation. We're going to be doing the differentiation rules, derivatives of trigonometric functions, and the chain rule. Are there any questions?